Very good morning, children. Welcome to 8th Standard Science. Children, today we are going to study chapter number 16 in science, that is reflection of light. And in this lesson, we will discuss reflection of light, regular and irregular reflection of light, making of kaleidoscope and periscope. For that, children, you are going to open your textbook and keep a pencil with you. Children, watch the video carefully by clicking the link.
How do we humans perceive the things around us? We have 5 senses that help us to interact with the world around us. These are sight, hearing, taste, smell, and touch. Eyes help us to see things, ears help us to hear sounds, we smell with our nose, taste with our tongue, and the sense of touch is provided by our skin. Of course, all senses are important, but the sense of sight is the most important. Here is an interesting fact. We perceive almost 80% of the world around us by using our sense of sight. We see objects around us with our eyes. But then why don't our eyes see these objects in the dark? The answer to this question is light. We are able to see the objects around us because of the light coming from these objects. The light from these objects travels in space and reaches our eyes. When it's dark or during nighttime, as there is no light, we are unable to see these objects clearly. Some objects can generate their own light. For instance, the sun, the fluorescent bulbs, burning candles can generate their own light. The objects which generate their own light are called the luminous objects. Almost all of the objects that we come across cannot generate their own light. The table, a chair, wall, paper are few of such examples. Such objects are called as non-luminous objects. But I just told you that we see objects around us because of the light coming from them. And if objects like these cannot generate light, then how come we are able to see them? We are able to see them because of the reflection of light. These objects reflect the light to our eyes. What light are they reflecting? Where is the light coming from? This light is nothing but the light coming from the luminous objects. So how can we summarize this? We are able to see non-luminous objects because they reflect the light of the luminous objects falling on these surfaces. Let me repeat. The light coming from the luminous objects falls on the non-luminous objects. Non-luminous objects then reflect this light, and this reflected light travels towards our eyes. And that's why we see the objects. In the daytime, we are able to see blue skies, the white clouds and the green grass because the light from the sun is getting reflected by them and traveling towards our eyes. At night, we are able to see the moon because it is reflecting the light from the sun. Note that moon is non-luminous and it cannot generate its own light. As I said earlier, most of the objects that we come across in our daily life are non-luminous. We only see them because they reflect the light. Step inside a dark room, light up a torch and point it at the distant wall. Look carefully at the path of the light coming from the torch. You will see tiny dust particles in the air. What is the reason for this? Why are you able to see these particles? You are able to see the dust particles because the light from the torch is getting reflected from their surfaces and traveling towards our eyes. We also see the same thing in a very dimly lit room where the only source of light is a small amount of sunlight coming from the window. In this video, we saw that the reflection of light plays an important role. It's because of the reflection of light that we are able to see most of the objects. In the next video, we will talk about the laws of reflection of light. In our previous video, we learned that we see objects around us because of the light reflecting from them. Some objects like the sun, burning candle and the fluorescent bulb emit light of their own. They are also called luminous objects. Many objects around us are non-luminous, that is, they cannot generate their own light. However, these objects reflect the light from the luminous objects from their surfaces. And because of this reflection, we can see such objects. In which direction do the luminous objects emit their light? They emit light in all the possible directions. Consider a fluorescent bulb which is glowing. It is emitting light in all the directions. Let us denote each direction with a straight line and an arrow on it pointing in the direction where the light is traveling. So all these arrows represent various paths along which light is traveling. These arrows are what we call rays of light. Here's how we define a ray of light. A ray of light is a straight line path along which light travels. So now we know that light emitted by luminous objects travel in a variety of directions. Suppose rays of light from this fluorescent bulb fall on the surface. It being non-luminous reflects these rays, and these reflected rays travel along a certain path. Consider this plane surface. Suppose one of the rays of light from the bulb strikes at this point. This is called an incident ray. We know that this surface will reflect this ray, and the reflected ray will travel in this direction. Why only in this direction? Why not here or here? This is because rays of light obey certain laws of reflection when they strike any surface. Draw a perpendicular to the surface at the point of incidence. This line is also called normal. Here are the two laws of reflection that any light ray obeys. To understand the first one, we first need to know what angle of incidence and angle of reflection are. The angle of incidence is the angle made by the incident ray with the normal. It is denoted by I. The angle of reflection is the angle made by the reflected ray with the normal. It is denoted by R. So our first law says that the angle of incidence is always equal to the angle of reflection. I is equal to R. Here, as I is equal to R, if the incident ray strikes at this point, then the reflected ray will travel along this direction only so as to keep the measure of R same as I. If I move the incident ray here, then the reflected ray will also move to keep the measure of R same as I. I is always equal to R. Okay, so this was about the first statement. What about the second statement? The second one tells us that the incident ray, reflected ray and normal all lie in the same plane. So if I draw this scenario on the piece of paper, I will get this. Incident ray, reflected ray and the normal, all three are in the plane of the paper. The second law tells us that they will always be on the same plane. For example, if the reflected ray is in this direction instead of this, then the diagram will look like this. The incident ray and normal are in the plane of the paper, whereas the reflected ray is not in this plane. This violates our second law, and hence this ray will not be reflected in that direction. This is just not possible. It can only be like this. I will be equal to R, and they will lie on the same plane. I hope both the laws are clear now. In the next lesson, we will see an experiment based on this concept which you can easily perform at home. In our previous video, we discussed the two laws of reflection. Today, we will do one cool experiment that you can do at your home to verify the laws. Cover a table with a white sheet of paper. Take a comb and cover all its openings except the middle one. You can use black paper to cover them. Place the comb perpendicular to the white sheet of paper as shown. Now light up a torch. Throw its light through the opening of the comb from one side. Adjust the torch in such a way that you should be able to see the light on the white sheet of paper. Next, we place the plane surface of the mirror in the path of this light. What did you see? Did the light get reflected? Yes, You can clearly see the reflection of light on the sheet of paper. Represent this light with the incident ray and reflected ray drawn on this white sheet of paper like this. Also draw a normal to the mirror surface. Remember, normal is a perpendicular line drawn at the point of incidence. What are these two angles called? This angle is called angle of incidence and represented by I, while this angle is called angle of reflection represented by R. Measure these two angles with the help of a protractor. The measure of the two angles will almost be the same. They are approximately equal. This is the first law of reflection. So with this experiment, you can verify this law. Well, if you're still not convinced, you can take further readings by changing the direction of the incident light. Change this angle of incidence by moving the comb slightly. Make sure that the point of incidence is the same in both cases. That is, this point here is same as it was previously. But notice that this time the angle of incidence is greater than the previous one. So by the first law of reflection of light, the angle of reflection should also be greater. And that is the case indeed. Measure both the angles and again you will find that they are approximately equal. Take 2 more readings to complete this table. Do you notice anything strange here? The first law tells us that angle of incidence is equal to angle of reflection and not approximately equal. Why am I using the word approximately? Well, there are chances of errors that may come about during measurements of things. We can refer to them as human errors. It also depends on narrowness of the light beam. Narrower this beam, more accurate will be the results. And this is the reason why we are passing a light through the small opening of the comb. Only a narrow beam of light from the torch passes through the small slit. This minimizes the error in the measurement. Also, one more thing that we need to keep in mind is that the beam of light is different from the ray of light. For example, in this experiment, the light you see is a beam of light. A ray of light is simply an idealization of a beam. We can see a beam, but we cannot see a ray of light. However, at this stage, we can think of ray of light as a narrow beam of light. And we will call this narrow beam a ray of light.
Good morning, children. Today we shall learn about the regular and diffused reflection. When parallel rays get refracted by a smooth surface, say like a mirror, they remain parallel even after reflection. This kind of reflection is called regular reflection. Here we can easily confirm that angle of incidence is equal to angle of reflection. So, regular reflection takes place when light is incident on smooth, polished and regular surfaces. When parallel rays get refracted by uneven surface, the rays get scattered after reflection. That is, they no longer remain parallel after reflection. This is called diffused reflection. When all the parallel rays reflected from a plane surface are not parallel, the reflection is known as diffused or irregular reflection. Diffused reflection takes place from rough surfaces. Now you might think, are the angle of incident and angle of reflection equal in the case of diffused or irregular reflection? We can't say that angle of incidence is equal to angle of reflection from this diagram, can we? But, you know, diffused reflection obeys the law of reflection too. Let us see this. We divide the uneven surface into small fragments and look closely. Take this ray in red color. We draw a perpendicular on the fragment of surface it got reflected from. Here, the solid blue line is perpendicular to the fragment of the surface and it is the normal. If we measure the angle of incidence, which is the angle between the normal and the incidence ray here, which is represented by angle I, and we also measure the angle of reflection, which is angle R, the angle between the normal and the reflected ray. So what do we find? Here we'll see that angle of incidence is equal to angle of reflection. This way, if we look into each pair of incidence and the corresponding reflected ray, we would find even diffuse reflection obeys law of reflection. So to sum up what we learned today, light is reflected from all the surfaces. Regular reflection takes place when the light is incident on smooth, polished and regular surfaces, whereas diffused or irregular reflection takes place from the rough surfaces. In both kinds of reflection, whether diffused or regular, laws of reflections hold.
Our topic for today is laws of reflection.
Good job.
What happened to our light?
No idea.
I have an idea.
Really?
Consider this ray of light which strikes a mirror. This ray of light is called the incident ray. The point at which the incident ray strikes the mirror is called the point of incidence.
Let's go up.
Draw a line perpendicular to the mirror through the point of incidence. This line is called normal. The angle which the incident ray makes with the normal is called the angle of incidence.
It's still not working.
My idea is not over yet.
When the incident ray strikes the mirror, it will bounce off the mirror. The ray which bounces off is called the reflected ray. The angle which the reflected ray makes with the normal is called angle of reflection. let us learn the two laws of reflection. The angle of incidence is always equal to the angle of reflection. If the angle of incidence is 30 degrees, then the angle of reflection will also be 30 degrees. Remember that these angles are always measured from the normal, not from the mirror. The incident ray, the normal at the point of incidence, and the reflected ray all lie in the same plane.
We learned that objects are visible because of the light getting reflected from their surfaces. This reflected light enters our eyes and we see that object. What happens inside the human eye when the light rays enter it? What is it that helps us see the things around us? The human eye is roughly spherical in shape. What we're going to do in this video is understand the different parts of the eye in short, not in extreme detail. Let's begin. The outer layer of the eye is called the cornea. It's white in color and transparent. Transparent? Yes, it means that it allows light to pass through it. It acts like a tough front wall of the eye. What is its function? It protects the interior of the eye from accidents and also does not allow foreign particles to enter the eye. Okay, so this was all about the outer layer of the eye. Let's now talk about the things present inside. Behind the cornea, there's a dark muscular structure called the iris. Iris determines the color of the eye. For instance, when we say that a person has blue eyes, it means that the color of the iris of the person's eye is blue. Now, there is a small opening at the center of the iris for the light to enter. Do you know what it's called? It's called the pupil. The iris actually acts like a shutter of a camera. It controls the amount of light entering the eye by enlarging or shrinking and thereby adjusting the size of the pupil. For example, when you focus the light from the torch directly into a person's eye, the iris shrinks. This is because the intensity of light is too much for the eyes to bear. The shrinking iris stops the unwanted light from entering through the pupil. And when it's dark or when there's less light, it expands, allowing more light to enter through the pupil. Okay, what happens next? The light that enters through the pupil falls on the lens kept behind. The lens is a convex lens. What is a convex lens? Convex lens is a lens which is thicker at the center than the edges. It's a converging lens. That is, it focuses all the light at one point. In a normal regular eye, this point is somewhere here on this inner boundary called retina. Why do I say a normal eye? Well, in a defective eye, this point of focus may lie either in front of the retina or behind the retina. We will talk about this defect of eye in our future videos, but first, let's go back to our normal eye where light is focused on the retina. Retina is at the back of the eye and marks the inner layer of the eyeball. Retina contains lots of nerve cells that sense the light. The nerve cells are of two kinds, namely cones, which are sensitive to bright light, and rods, which are sensitive to dim light. The message or sensation is then transferred to the brain along the optic nerve. Okay, let's quickly recap what we learned about the human eye. Human eye has a roughly spherical shape. The outer part of an eye, called the cornea, is a thick white transparent wall which protects the eye from accidents and keeps the foreign particles from entering inside. Behind the cornea, the colorful part of the eye, called the iris, is present. It has a small opening at the center called pupil. Iris controls the light entering through the pupil by contracting and expanding. Behind the pupil, there is a converging lens which focuses the light on retina. Retina consists of two types of nerve cells, namely cones and rods. They transfer the message through the optic nerve. There is a lot of information to digest, so we will stop here and continue to learn more about the eye in the next lesson.
You learnt about the law of reflection. Can you think of any instances where it is put to use? If I give you a couple of mirrors and ask you to watch your friends without you being seen, what will you do? Periscope and kaleidoscope are useful examples of the law of reflection at work. Let's understand these and build simple version as well. A periscope lets you look around walls, corners or other obstacles. Submarines are under the sea level most of the time. Submarines have periscopes so that people inside can watch what is on the surface of water. Periscope is based on law of reflection. It consists of reflecting mirrors at opposite ends of the tube container. It is important that the mirrors are placed at 45 degrees of angle. Because light always reflects away from a mirror at the same angle that it hits. In a periscope, light from an object strikes the top mirror at 45 degrees and bounces off at the same angle. This sends light directly down the tube and onto the lower mirror. This mirror, also at 45 degrees angle, reflects light directly to your eyes. Some advanced periscope use a combination of lenses and mirrors to achieve better results. Activity. We can construct basic periscope with A4 size card sheet paper and acrylic mirrors. Paper is folded into square tubing. 2 openings are made at the opposite side, and 2 acrylic mirrors are inserted such that they are at an angle of 45 degrees to the side walls. One opening points towards the field while the other is used to observe the field. If you don't have acrylic mirrors, you can also build similar one with regular glass mirrors. Try changing the angle of one mirror or both mirrors and check if periscope still works. Can you build similar periscope which will allow you to see behind you? Kaleidoscope is a perfect blend of art and science, which means instrument for viewing beautiful forms. You would have probably seen one of these in your childhood days. Since its invention around 100 years back, many variations of these are available in the market. There are generally 4 basic components of kaleidoscope: eyepiece, external body, mirror system and object chamber. It is the mirror system that creates the magic. The mirror shape, the number of mirrors used and the angles at which they are joined combine to produce an image you see. When 2 mirrors are used, they are arranged in V shape. 3 mirror system can be arranged in any form of triangle as long as sum of 3 angles is 180 degrees. Most popular ones use straight mirrors in an equilateral triangle. Object chamber holds objects which are replicated by mirrors. These are normally colorful, small, translucent. These might be plastic or glass beads, chips, seeds, crystals and marbles, and the list is endless. The colors, shapes, forms, patterns combine in ever-changing, never-repeating relationship. Let us build a basic kaleidoscope. We will use 3 acrylic mirrors and tie these with rubber bands. Instead of using conventional objects to create pattern, we will use paper and draw various patterns with sketch pens. Paper disc painted from inside is locked in a toothpick attached to one mirror. With one eye closed and other placed inside the triangular cavity, kaleidoscope is pointed at the light source. Paper disc is slightly rotated to generate different patterns. This arrangement enables us to build kaleidoscope quickly and explore different patterns. If acrylic mirrors are not available, you can use regular glass mirrors as well. Try with different shapes, colors to get beautiful patterns. Try building kaleidoscope with 4 mirrors. Summary. We learnt about functioning of periscope and kaleidoscope and build simpler ones using everyday things. Introduce variations and try building your own.
Okay, so children, I hope you all have understood the chapter well. Here are some solved numerical examples are given, children. So we'll just see the first example, that is if the reflected ray makes an angle of 60 degree with the normal. So what angle must be the incident ray with the normal? Okay, so what are the given values? Angle of reflection, that is angle of reflection is 60 degree. Angle of incidence is we need to take out. So according to the law of reflection, angle of incidence is equals to angle of reflection. In this way we will get the answer. The incident ray will make an angle of 60 degree with the normal. So as it is, you are going to solve all the examples. Children, solve the exercise by given PDF. Okay children, thank you.